really don't feel good. It's okay. Where are my pens? It's like, I'm going to go grab a pen. Okay, I'll be right back. So I got pens. And it looks like pretty much everybody's here. Yeah, so first, I'm sorry it took me so long to get those exam scores in there. I did have them graded Thursday. But I just didn't get around to actually putting the damn things into Canvas until Sunday, and I'm sure that was frustrating to some of you guys, so I apologize for that. They are in, and the scans with written feedback are coming behind them. So I'll have those in there soon too, so you can take a look and see exactly why each point went where it did. And if you want to go over them with me, I'd be happy to do that as well. In the meantime, we are going to keep learning about integrals. So. Today is the 3rd, so we are all the way into August now, which is crazy. How fast this time has gone by. Gee, I would have to take a look at, I'm not sure what you mean by a note for SG2. So I haven't, the grades, I haven't graded the second study guide yet. So I graded the all the exams and the first study guide. But study guide 2, that grade will be still coming. But don't panic about them. Like I said, and like you can probably see from the past one, it's not about correctness so much as it is about completeness. As long as you give me a solution for each problem, you're not going to lose points on the study guide. The purpose of the study guide is to let me see and get a feel for your work in a low pressure situation. So if you're nervous about the study guide grades, please don't be. As long as they were complete, they'll get full credit. The only time I take points off there are if there are problems just straight missing, or solutions that are like obviously speed copied out the back of the book or something like that. Okay. So the way, Zach asked a good question in chat, and it's one that I answered in passing last week, but I want to be clear about it. So the homework that I'm going to release this week is going to count for your study guide 3. So as you work through the homework that's opening up today, this last homework set that we have, make sure you write out solutions to those problems. Those solutions you will scan and submit for your study guide 3. So what I didn't want to do is stack a bunch of shit on you at the end. I don't want you to have, a homework, a take-home test, and a study guide that you need to be doing all while also preparing for the final, because that feels like it's too much. But what I think would be fair is to have this study guide 3 just be your written solutions to the last homework set. So as you work through this last homework set, make sure that you're writing out full solutions, and then you can scan and submit those for study guide 3. Layla, I'm not sure what the, will not review questions from exam 2. Oh, like going through a key. No, I didn't intend to, or I haven't gone through a key for exam 2 because we had people up until last Friday who still had not taken their makeup, and the makeup version is similar enough to the original version that I don't want to post videos without full solutions to those before somebody else took them. Okay, yeah. But no, I would be happy to go over any questions you guys have from exam 2. Office hours would be the best place for that though, yes, because we do have more class material that we need to get through. So if you'd like to see a solution to an exam 2 problem, come by office hours with it. And yeah, I would be happy to go over it. Okay. So maybe I'll say some of this here, right? The study guide. 3 grade in Canvas will come from written solutions to this week's homework. I think is homework 11. And I'll put a little note in WebAssign that says like homework 11 / study guide 3 to make sure we remember. And then exam 3. Take home. Which I will give out this Friday. And that should be 8/8, I think. 7.
So it's homework 11 and exam 3. We have to write down and scan and send to you.
Correct, yes.
Okay.
Yeah, so homework 11 will also count as study guide 3. And that way I'm not piling you guys up with lots and lots of stuff while you also want to be studying for the final. And because there's really not a whole lot on exam 2 that's not on exam 2, right? Just the last 2 weeks worth of material. So this week's homework will encompass the full feel of exam 3. And I want to make sure that you do have something like that, but I also don't want to stack you with too much stuff to do as you're getting ready for the final. And then exam 3 itself will be that take home that we talked about last week. I'll give it to you this Friday, and it will be due the following Tuesday, which is the 11th, the day of the final. Okay. So what we've been talking about, let me actually start a fresh page. Last time, we introduced the following theorems. These are fundamental theorems of calculus 1 and 2, FTC1 and FTC2. The first fundamental theorem which I abbreviate FTC1, both of these tell you how the derivative operation is related to the integral operation. And that's why we call them the fundamental theorems of calculus, because the two fundamental operations of calculus are differentiation and integration. And these theorems tie those together. The first one says if f of x is continuous, and if you want to be careful about it, you could say continuous on the interval AB. Then the new function, which you could call g of x, defined as the integral from a to x of f of t dt, and we use a different variable here than here because we don't want to confuse somebody. Remember, this is like the area underneath f from a up to x, and that's how we define this new function g. We played with this quite a bit last time. Then this is not just continuous, but also differentiable. And here we would say it's differentiable on the open interval AB. And the derivative g primed of x is actually f of x. So in other words, g is an antiderivative for f. And there are some specific problems where we use this relationship that g prime defined this way is f. There are some ways we can use it with the chain rule that are a little bit surprising, can make for some challenging problems. So I'd like to work an example or two like that. The second fundamental theorem of calculus this guy just says if f of x has finite discontinuities only, and capital F is an antiderivative for little f, then the integral from a to b of little f is equal to capital F evaluated from a to b. And there was some notation for this. You'll see me write this a lot. So you put the antiderivative in some brackets, and then on the right side, you put the two, we call them bounds of integration. And that just stands for capital F of b minus capital F of a. So this second guy, we got a fair amount of practice using him last week, calculating some integrals by finding an antiderivative and evaluating between endpoints. We haven't really gotten to practice this one much, and I'd like to do a little bit of both. So give me just 1 second here. Pull up textbook. Definite integrals, you sub, yeah. Yeah, no, that's it. All right. Oh, I keep closing that on accident. Yeah. Okay. So let's take a look here. Your textbook has a lot of useful pictures and things that'll help you understand, just like that graph where we drew F and G last time. You can compare the two here, right? So here's calculating G from F, looking at the graph of G. Statement of the first theorem. So the examples. Yeah, some of these are cute. So let's grab one of these slightly challenging FTC1 examples, like example 4 here. This looks good. Maybe I'll do a simple example and a hard one. Okay. So I'd like to leave this somewhere you can see FTC1 as we work an example or two. So suppose I define some function f of x as the integral from 1 to x of, what do we want to do here? How about tangent of x, because our tangent of theta, d theta. So we don't actually know how to integrate the tangent function yet. Evaluating this integral isn't something we know how to do. I don't know an antiderivative for tangent. Here, I started writing the wrong variables, so just, yeah, you can ignore that. But this is tan theta d theta integrated from 1 to x. That's how we define f of x. And the question is, can we find f prime of x? So I'd like to compare what we have here to FTC1, in particular this. This says if you define some function as the integral from a constant up to x of some other function, then the derivative of the new guy is just the old guy. So if I apply FTC1 to this problem, then I'd say f primed of x should just be tangent of x. Startlingly simple, right? Another way to say the first fundamental theorem is that d dx of the integral from a to x f of t dt is just f of x. So the way most people read this is that integration and differentiation undo each other. So this f prime of x is definitely tangent of x. So the thetas go away. That's the idea, is that you take whatever it is that's up here and you plug it in here, and that will be your derivative. So d dx, the derivative taken with respect to x of the integral from a to x of f of t dt, or f of whatever it is, you could use some other variable down here. You would still just get f of whatever this variable is up here. And I like writing it in this fashion, like I've got it down here on the bottom, because that helps me see what's really going on. If you take a derivative of an integral, they kind of cancel each other out, and you just get the function that's inside. But the variable that you plug into the function that's inside is the upper bound here, the guy that's used to define the new function. Okay. Let's look at another one. So if g of z is the integral from e to z of ln x dx, can we find g primed of z? So the trick is just to remember that G primed is what you get by applying ddx to G. So that's, or in this case, sorry, ddz, because the variable for G is Z. So this would be ddz integral e to z ln x dx. And then just like in this statement here, the variable we're differentiating with respect to is z, and the upper limit of integration is z. So the differential operator ddz and the integral cancel each other out, and we'll just get ln of z. What this says is if you could do the integral and then differentiate, this is what you would get. We don't know what the integral of ln x is, so we can't actually do the integral yet. I can prove FTC2 or FTC1 for you using FTC2 if you feel like it would help. But for most people, I think it's just a matter of kind of recognizing and getting used to the pattern. So if you want to differentiate through an integral, you'll just get the function inside. And then it's a matter of what variable do you plug in? Oh, well, it's whatever one the differential operator is using, as long as that guy shows up as the upper limit on the integral also. So because this is g of z, and this is a z up here, g primed of z will just be this function with that variable plugged in. Let's look at a quick proof. I don't think it'll hurt. Of FTC1. It uses FTC2. We want to show that if g of x is the integral from a to x of f of t dt, then g primed of x, which is ddx of g of x, which is ddx of the integral from a to x of f of t dt, we want to show that this is is f of x. And the way we can do this is by using FTC2. By FTC2, the integral from a to x of f of t dt is equal to capital F of x minus capital F of a, where capital F is an antiderivative for little f. So now, if I take this and I differentiate it, what do I get? Therefore, g primed of x, which is, remember, ddx of the integral from a to x of little f of t dt, well, that's just ddx of this, according to FTC2. So that's ddx of capital F of x minus capital F of a. The derivative of capital F is capital F primed of x. The derivative of capital F of a is 0 because it's a constant. And capital F primed, oh, that's little f, because capital F is an antiderivative. So that's it, that's the proof. So you can kind of see what's going on in the background in these problems if you think about them like that. If we knew what capital F was for ln x, then this integral from e to z of ln x dx would be capital F of z minus capital F of e. Capital F of e would be a constant, so his derivative would be 0. Capital F of z is an antiderivative for ln x, or an antiderivative for ln z. It's an antiderivative for the natural log function. So when you differentiate it, you would get the natural log back. And that's what we're doing in this proof, right? By FTC2, the integral from a to x of little f is capital F of x minus capital F of a. You find an antiderivative and then you evaluate between bounds. That's what the second fundamental theorem says, and that's what we got all that practice with last week at the end of class. So if I come through this line and I differentiate everywhere with respect to x, on the left-hand side, I'll get this, which is the thing I'm trying to calculate. It's the thing I'm trying to show is little f of x. But I don't know that yet. I need to show that. On the right-hand side, though, I get ddx of this stuff. ddx of capital F of x is capital F primed of x. ddx of capital F of a is 0 because a is a constant, so capital F of a is a constant. So you get capital F primed of x minus 0. But then remember what capital F was. Capital F is an antiderivative for little f, which means capital F primed is little f. And thinking about it this way will make the harder FTC1 problems a little bit easier to see. So let me modify each of these examples that we just did to make them a teensy bit tougher. And let's see if we can't, through this lens, manage those. So instead of looking at this, maybe I define little f to be the integral from 1 to x squared of tan theta d theta. And I say, okay, let's find f primed. So this no longer looks exactly like my FTC1. In fact, what I need here is the chain rule. I want to say, by FTC1, I can just take this and plug it in here. That f primed of x is tan of x squared. But that's not quite correct. What is correct is this times the derivative of x squared. It's an application of the chain rule in a way that's not entirely obvious. So you can think of this whole thing as your outer function and this guy as your inner function. And this is because if, call it capital G of theta is an antiderivative for tan theta, then the integral from 1 to x squared of tan theta d theta would be capital G of x squared minus capital G of 1. So the derivative here, ddx of integral 1 to x squared tan theta d theta would be ddx of g of x squared minus g of 1, which would be g primed of x squared times 2x by the chain rule minus 0. But g primed of x squared, remember g is an antiderivative for tangent. So g primed is tangent. So this is tangent of x squared times 2x, which is what we claimed at the start. So these slightly more complicated FTC1 problems where the upper bound for your integral is not just x or z or whatever the variable over here is, but is some function of that variable, you need to multiply by the derivative of this guy to satisfy the chain rule. And if you're ever uncertain, you can always go through it like this. Thing is, you just have to have enough imagination to go, okay, well, I don't know what an antiderivative for that function is. Let me just pretend like I have one, give it a name, and then I can work with it symbolically. So here, if g, capital G, was an antiderivative for tan theta, then by FTC2, I could evaluate this integral by evaluating the antiderivative at these endpoints. Even though I don't know what capital G is, I can still write it down like this and then differentiate on both sides. And then I get what we claimed to have gotten. I think most students, though, just kind of memorize the pattern. So questions on this and how it relates to the original one?
So we want to like plug it in and then take the derivative?
Yeah, so normally to differentiate through an integral, you'll just take this guy and plug it in here. If this guy happens to be at all complicated, you also need to multiply by his derivative. That's the feel.
Cool, thank you.
Yeah, it's not too bad. I remember when I learned this stuff for the first time, it didn't really make sense to me. It was something that I just kind of had to do. And I remember my classmates saying the same sort of thing. But then when I started thinking about it like this, which admittedly didn't come for a few years. I didn't think of this way of explaining what's going on here until I started tutoring this a little later as an undergrad, and I had to explain it to other people. But this is what eventually made it clear to me. I know for most people at this stage, you're just thinking about it like this. You're just gonna plug this guy in here. And then if this is complicated, remember to slap on his derivative. So you can always try this, right? You can always just plug this guy in here and then multiply by his derivative. And if that wasn't needed, then this derivative will be a 1, like it would have been here, right? So here, if I just plug this guy in here, I get tan x. And then if I was nervous and I was like, oh, is this that thing where I need to do the chain rule and I need to multiply by the derivative? Well, the derivative of x is just 1. So you could, if you did also multiply by the derivative of the upper limit here, it wouldn't get you in any trouble. All right, una más. Let's let f of x be the integral from 2 to secant x of the natural log of t plus 1 dt. And find f primed of x. So since what I'm after is f primed, that's the derivative of this function, which is defined as an integral. I know that the derivative and the integral are going to eat each other up, and I'll just get like natural log of secant x plus 1. So I just plug the upper bound here in for the variable here. So by FTC1, f primed of x should be equal to the natural log of secant x plus 1. And then I ask, okay, well, is this one of those weirder things where this is a little bit complicated up here? Yeah, this isn't just an x, this is a secant of x that I've plugged in. So I'm going to need to multiply here by the derivative of secant x. And the derivative of secant x is secant x tangent x. So that's my derivative. I recommend reading the section 5.3. I don't think that just watching me solve a few problems and state the theorems, even with that little proof, will be enough to digest it all the way. But if you take your time, thinking about these examples and then go through and read the textbook, maybe rewatch the video, it will sink in eventually. And the way I encourage you to think about it is the way I was just showing you, where you pretend you have an antiderivative that you can play with, and then you'll be able to reason your way there rather than just having to memorize. But the big game moving forwards is not FTC1. FTC1 is all well and good, but the really important thing as we move forward here is FTC2. And FTC2 gives us a way of evaluating integrals. So you'll see plenty of examples like this. And then we get to FTC2. We introduce a few different notations. I think we did the 1 over x integral last time. We did the cos x integral last time. We should do some more challenging things. So here's some derivatives like that. Yeah, let's do a handful of these. 0 to 1, x to the e to the x, that looks like fun. Okay, so let's get some practice with FTC2. Here I'm being asked to just straight up calculate an integral, right? Find the value of this integral, which is the area under this function from 0 to 1. So I know what I need to do. I need to find an antiderivative for this function and then evaluate that from 0 to 1. Normally the way we would do this is by using the properties of the integral to split it up and handle each one on its own. So that's the integral from 0 to 1 of x to the e dx plus the integral from 0 to 1, integral 0 to 1 e to the x dx. So just like if I was differentiating this function, I could split it up and take the derivative of each on their own. When I'm integrating, I can split it up and take the integral of the first function and then add that to the integral of the second function. In other words, these parentheses here matter, right? You should always remember to write your integrand, the thing inside your integral, in parens, because the integral symbol kind of distributes and the dx kind of distributes. It follows the normal looking algebra rules. So as long as you always write these parentheses, I don't think you'll ever have a hard time noticing that you can do this. And then I need one of my antiderivative rules for this guy. I need a different antiderivative rule for this guy. So what sort of function is x to the e? Which one of our antiderivative rules could I apply to this piece?
Are we doing e plus 1 over e plus 1 or no?
Very good. Yeah. That's it.
Sweet.
That's the power rule thing. So I want to find a function who has x to e as his derivative. Since that's a power function, I know that if I take a derivative of something that looks like this, I would subtract 1 from the power and then multiply by the old power. So here what I need to do is add 1 to the power and divide by that new power, because e is just a constant. So we antiderive this the same way we would antiderive x squared or x cubed. You add 1 to the power and then divide by that new power, just like Angelica said. And then because we're working with this definite integral here, we'll evaluate from x equals 0 to x equals 1. What about the e to the x integral? What is an antiderivative for e to the x?
Still just e to the x, right?
Yeah, e to the x is its own derivative, so it's also its own antiderivative. And this is why mathematicians are so in love with the function e to the x. You might have wondered. Yeah, this is it. All right. So I need to evaluate both of these pieces from 0 to 1. Here, if I plug in 1, I get 1 to the e plus 1 over e plus 1 minus, I plug in 0 to the e plus 1 over e plus 1. And it's always plug in this guy for x and then subtract what you get when you plug in the bottom. The order matters. And then here we'll have e to the 1 minus e to the 0. 1 raised to the e plus 1 power, that's still just 1. So this is 1 over e plus 1. 0 raised to the e plus 1, that's 0. Plus, and then here, e to the 1 is e, and e to the 0 is 1. So this is the value of that integral. Not too bad. Any questions on any of these steps?
Can you repeat that last simplification, please?
So 1 raised to the e plus 1, that's just 1, because 1 raised to any power is just 1. 0 raised to the e plus 1, that's 0. So the numerator here is 0. So this whole piece here is 0. So he goes away. E to the 1, that's this guy, it's just e. And e to the 0, that's 1, because anything raised to the power of 0, except for 0 itself, is 1.
Cool,
So
thank you.
it goes away. This is e, this is 1, and this is 1 over e plus 1.
And we kind of want to think of it as final minus initial in sense of from 0 to 1.
Yes, always
Okay.
plug in this guy, then subtract what you get when you plug in this guy. If you switch the order around, if I did these guys in the opposite order, everything would come out negative, because when you flip over a subtraction, like 3 minus 1 is 2, 1 minus 3 is negative 2, when you flip the order of subtraction, it changes the sign overall. Let's try one more in this vein. How about the integral from 0 to the square root of 3 of 8 over 1 plus x squared? So at a glance, it's not obvious what an antiderivative for this might look like. But like we started here with some rules for the integral, we can start here with some rules for the integral. In other words, we do a little bit of algebra. So this is the same as the integral from 0 to the square root of 3 of 8 times 1 over 1 plus x squared dx. Right, having an 8 upstairs is the same as having an 8 out front. Because if you wanted to multiply these two fractions, this would be like 8 over 1 times 1 over this. So the denominator would stay this, and the numerator would become 8. So I can pluck that constant off the top. And then one of my rules for integrals is that if I have a constant multiple, it has to be a constant. But if I have a constant multiplying my function, I can pop that outside the integral as well. So the 8 can come outside. And now I have to think of an antiderivative for 1 over 1 plus x squared. Who differentiates to that? There's no more
Natural log.
Not quite. 1 over x, natural log x has derivative 1 over x. Natural log 1 plus x squared has derivative 2x over 1 plus x squared. We actually saw that on our exam. So a natural log won't work for this. The only time natural logs work is for 1 over x. So think a little bit harder. Who have we seen that has this as his derivative? Think inverse trig.
Inverse tangent.
Yeah, good. The inverse tangent function has derivative 1 over 1 plus x squared. So inverse tangent is an antiderivative for 1 over 1 plus x squared, which means that 8 will come along for a ride, and I get arctan, or tan inverse of x, evaluated from 0 to the square root of 3. So the arctan integrals here are a family of things that you can spot quite quickly, which otherwise are a little bit tricky. And then if I evaluate here, this will be 8 times arctan of root 3 minus arctan of 0. So that's 8 times. Can anybody help me with the inverse tangent of root 3? What is that?
That means 1 over 1 plus root 3 square.
So I'm not trying to take a derivative now. I just want to know, what is this number? Like if you plug square root of 3 into the inverse tangent function, what do you get out? Or for what angle between negative pi over 2 and pi over 2 is the tangent of that angle equal to the square root of 3?
Is it pi over 4? I don't have my circle on me, but
Pi over 3 this time. So pi over 4 is exactly halfway through quadrant 1. So the inverse tangent of 1 is pi over 4. And the inverse tangent of root 3 is pi over 3. And then what is the inverse tangent of 0? For what angle between negative pi over 2 and pi over 2 is the tangent of that angle equal to 0? So again, you want to think of your unit circle. This one turns out to be 0. So here you get 8 pi over 3. Okay. Moving forward to the end of Calc 1 and also the first few months of Calc 2 is all this stuff, right? It's this stuff over and over and over again. Lots of tricks and ways of managing things like this. So this is stuff you want to get good at. It's stuff you're going to want to practice. I teach a lot of Calc 2. And I can tell you for sure that like not being comfortable with trig and inverse trig derivatives, not being comfortable with the unit circle are the #1 things that catch people out in the first few weeks of Calc 2. Alrighty, so this fellow is done now. Any questions about any one of these steps? Okay. I did see 1 or 2 other problems in there that I want to give you a taste of before we move on to the new stuff. Grab it exactly as it is from your text. This one looked good. V cubed plus 3v to the 6 over v to the 4 from 1 to 2. Okay. So let's see if we can do the same thing here. Let's see if we can find an antiderivative and then evaluate between those bounds. Just like in the last couple guys, the trick is going to be to simplify using algebra and properties of the integral until we get this down to some things that we can spot antiderivatives for. Certainly right off the top of my head, I have no idea what an antiderivative for this function looks like. But there's lots of algebra I can do. First, remember, I can split up fractions across their numerator. So I can take it as this over this plus this over this. So that would be my first step. Rewrite this as the integral from 1 to 2 of, and we always want to put our integrand in parentheses. That'll be v to the 3 over v to the 4 plus 3 v to the 6 over v to the 4 dv. So I just split it up like this. And imagine adding these two together, they already have the same denominator, so they'd just be the numerators added. You can run that backwards to split up. And then I can simplify this, and I can simplify this. V to the 3 over V to the 4, there's one more copy of V downstairs there than there is upstairs, so I can cancel 3 of them, and I'll be left with 1 over V. Here, on the other hand, I've got 2 more copies upstairs than I have downstairs, so I can cancel 4 copies, and I'll be left with 3V squared upstairs. So here's where our natural log is going to get to come in play, because I've got a 1 over V. We can split this into 2 different integrals and handle each on their own. So that's integral 1 to 2, 1 over V, dV, plus 3 times the integral from 1 to 2 of V squared, dV. So I split this up, gave each their own integral, and then in the second integral, I popped the 3 out, because the 3 is a constant multiple. So this is how this integral splits up. And now this guy, I can find an antiderivative for. That's my natural log. This guy, I can find an antiderivative for. That's a power rule thing. So I'll get the natural log, and we like to write absolute values here, from 1 to 2. That's my first guy. Plus 3 times. Now an antiderivative for V squared is V to the 3 over 3, evaluated from 1 to 2. So this piece becomes this piece, because the natural log of the absolute value of V is an antiderivative for 1 over V. And this piece becomes this piece, because an antiderivative for V squared is V cubed over 3.
I'm a little bit confused on what you did on the third step there.
From here to here.
Back from the top second line, yeah, there, from there to the.
I canceled as much as I could here, and I canceled as much as I could here. So this is like x cubed over x to the 4. That's x times x times x, or v times v times v upstairs. And this is v times v times v times v downstairs. So each of the 3 copies of v upstairs, I can cancel with a copy of v downstairs, and then I'll be left with 1 more downstairs.
Oh, okay. I was thinking you pulled something out.
No, or you could think of it as like the division power rule thing. So if I've got v to the 3 upstairs and v to the 4 downstairs, I'm dividing like bases so I can subtract the powers. That would be the same as v to the 3 minus 4. 3 minus 4 is -1. So this is the same as v to the -1, or 1 over v. I prefer to think of it as canceling, but either way is okay. And then the same thing here. I've got v times v times v times v times v times v upstairs, and I've got v times v times v times v downstairs. So I can cancel all 4 of the ones downstairs, and I'll be left with 2 upstairs. Or if you want to think of it as that power rule, this should be the same, because I'm dividing like bases, should be the same as v to the 6 minus 4, and 6 minus 4 is 2. So in other words, no calculus in that step, just algebra. Are we comfy here?
Yeah, I'm good. I just missed a step there.
No stress. What about from here to here? Does everybody see what we did here? We did 2 things here. We split up the integral as integral of this plus integral of this. And then I also took the 3 out from the second integral and popped it out front. So I'd have integral from 1 to 2 of 1 over v dv plus integral from 1 to 2 of 3v squared dv. That first integral is just right here, unchanged. That second one, integral 1 to 2 of 3v squared dv, has a constant multiple of 3 that can come out front the integral. So I had to split it up before I could pull that constant multiple out because this guy is not being multiplied by 3. Only this one is. So first we split, then we pop out. And then finally our antiderivative step. This is a power rule antiderivative. We add 1 to the power and divide by the new power. So that's going to be v cubed over 3. And this one is straight from our table. 1 over v has as its antiderivative natural log of absolute value of v. And now I just plug in. So this is ln absolute value of 2 minus ln absolute value of 1 plus 3 times 2 cubed over 3 minus 1 cubed over 3. And this is a cubed. This is the same as regular old ln2 minus ln1 because those numbers are positive, so their absolute values are just themselves. And this is 3 times 8/3 minus 1/3 because 2 cubed is 8 and 1 cubed is 1. ln1 is 0. ln2 is just ln2. There's nothing that we can do with that. Plus 3 times 8/3 minus 1/3 is 7/3. So this is ln2 plus 7. So you'll see a lot of problems like this in your homework this week, where you need to do some algebraic simplification, and then your antiderivatives are very straightforward. Anytime, just like when we talked about how to take derivatives of complicated functions, if you can simplify them algebraically first, you should, because the cleaner and simpler the expression is that you're trying to do the calculus to, the easier the calculus will be. So this is a fairly complicated looking object. I want to simplify it as much as I possibly can before I have to find an antiderivative. And this is as far as I could simplify that. I think this looks much simpler than this for a few reasons. First, you've got 2 separate pieces that you can handle on their own. And each of those pieces is a straight power function. This is v to the -1, this is v to the +2. So we know how to antiderive all power functions. Here you've got like a complicated looking rational function. It's not obvious that it's going to simplify to something so nice. But when we start playing around and doing the natural simplification stuff, it does land here. So you'll have a handful of problems in your homework this week that look like this. There's one other thing I wanted to show you today, and it's going to go fairly quickly. So maybe it's worth doing something a little bit more exciting. Yeah. Switch the region closed on one level. Is this going to go down? Error function, no. Sync function, maybe. Let's not stray too far from the skills we want to practice. We don't want to overwhelm. There are some properties of the integral that I want to highlight here. So let's look at that one. Okay, any other questions on this example? We're all totally comfy with everything that happens from here on? there is something I'd like to point out. Notice that this 3 out here ended up canceling with this 3 down here, right? We had 3 times 7 over 3, and we could cancel those 3's, and we just got this 7. It's actually possible to cancel the 3's earlier. And sometimes doing stuff like that can be very helpful. So my note here is that if we look at that piece on its own, we could have done the cancellation a little bit sooner. 3 times evaluation bracket v cubed over 3 from 1 to 2 is the same as 3 times evaluation bracket 1/3 v cubed from 1 to 2, because v cubed over 3 is the same as 1/3 times v cubed. Right, dividing by 3 here is the same as multiplying by 1/3 here. And then this constant can pop out of the evaluation bracket. So I would have 3 times 1/3 times v cubed evaluated from 1 to 2. And now these could cancel. 3 times 1/3 is 1. So this would be 2 cubed minus 1 cubed, which is 8 minus 1, which is 7. So we could have gotten it that way, and sometimes this is a little bit quicker. So you can pop constants out of these evaluation brackets, or if you want to think about it the other way, you can bring constants into the evaluation bracket. So I could have also thought of it like bringing this 3 inside to cancel with that 3. But most people think of it like this, and sometimes this can be helpful. So I just wanted to point that out, that the 3 here and the 3 here cancel. And instead of canceling them at the end like this to get the 7, I could have canceled them at the start. Could not have canceled them before this step though, because that 1/3 showed up here as the antiderivative. So the soonest place I could have canceled them is here. In other words, this evaluation bracket thing is itself a linear operator. Constants pop out of evaluation brackets, and you can split evaluation brackets up over addition and subtraction. So the general note is that if you have like 2 functions evaluated from A to B, that's the same as evaluating their sum. And constants can pop out. So the algebra of these evaluation brackets works like this. It's the bottom feature that I was highlighting there on the right. The top feature we could use, we haven't used it yet, but we could use anytime we wanted. So sometimes these things are easier to evaluate in chunks like this rather than all together. And sometimes popping a constant out of the evaluation brackets is useful because you might get cancellation like this. Okay. Let's see, I don't want to scare anybody too bad. Integrals certainly can get hard. Maybe we'll do one more little example. How about let's look at this. So I'd like to evaluate the integral from 1 to 3 of x e to the x minus root x all divided by x. And just like in the last problem, I have no idea what an antiderivative for this thing might look like. So I want to split it up and do as much algebra as I can. I want to simplify this as much as I can and then find an antiderivative. Can I cancel this x with this x as it's written right now?
Nope.
Yeah, no, why not? It's correct that we can't. I'm curious why.
Because it's connected to things.
Yeah, I would need, if I could factor an x out from the top, I could write this as x times parentheses some shit. Then I could cancel that x. But right now, this is not a factor of the top. It's just attached to this guy. So before I could do any cancellation, I need to split this up. So that's what we're going to do. This is x e to the x over x plus square root of x over x.
Isn't it minus?
Oh, sorry, minus. Yeah, thank you. Good catch. So while I couldn't cancel this at this stage because I don't have a copy of x here to factor, I can cancel these guys now because x is a factor of the numerator of this little fraction and it is a factor of the denominator of this little fraction. So those x's will cancel. Here, I'm going to have to do something else. So let's do this in pieces.
Mr. P, I have a question.
Sure, go ahead.
The antiderivative, that s, how come it's 2 instead of 3?
Oh, it should be 3. Yeah.
Oh,
Oh, yeah, that should not have changed. Sorry, I just copied it down wrong. Yeah, so the upper bound for both of these is 3, just like in the original. Thank you. Okay, so I split that fraction apart across its numerator. And then in this guy, I'm able to cancel the x's. So I just get e to the x. E to the x over 1 is e to the x. How could I hope to simplify this piece? So if I step to the side and just do the algebra here, that's x to the 1/2 over x to the 1. That's the same as x to the 1/2 minus 1, which is x to the negative 1/2. So I get integral 1 to 3 e to the x minus x to the negative 1/2 dx. And now I can split this up. Integral 1 to 3 e to the x dx minus integral 1 to 3 x to the negative 1/2 dx. And each of those I can apply the appropriate rule to. So I have a rule for this guy. I have a rule for this guy. Antiderivative for e to the x is definitely just e to the x. So that first integral is e to the x from 1 to 3. And then the minus comes along. How do I find an antiderivative for x to the negative 1/2? That's a power rule thing.
Yeah.
Just like the same way we find an antiderivative for x squared or x cubed, you add 1 to the power and divide by the new power. So negative 1/2 plus 1 is positive 1/2. So this will be x to the positive 1/2 divided by positive 1/2. And there's nothing wrong with writing it like that. Some people try to rush and simplify this fraction. it's okay to do that also. Just make sure that you're being very careful. And if you're at all uncertain, go ahead and take the step where you write it like this. So we'll get e to the x from 1 to 3 minus, now I'll simplify, that's 2 times the square root of x from 1 to 3. So I flip and multiply this 1/2 and I get a 2. And then x to the positive 1/2, that's the same as the square root of x. So at the end of the day, this will be e cubed minus e to the 1 minus, I can pop the 2 out, and I'll get the square root of 3 minus the square root of 1. And these are being subtracted. The square root of 1 is a nice number, so I guess we could clean that up a little bit. We can distribute the -2. So I get e cubed minus e minus 2 square roots of 3 plus 2, because this piece is 1. And the negative makes positive. Okay. This is a fair amount of practice for what we've done, what we've learned so far. There's 2 more big things I want to teach you this week. One of them is very easy, indefinite integrals. The other one, less so. So first, questions on what we did here. It's just another example, kind of like the one we did before. We're going to split it up and do whatever algebra we can at the start. Any steps we'd like to take a closer look at? As you go through these problems, I recommend that you try to write things the way I'm writing them, right? So be very careful with the parentheses. Be very, very careful with your notation. As you're getting ready to move into Calc 2, the quality of your notation matters a lot. As you can imagine, these problems can get very complicated. It's not uncommon for a Calc 2 problem to take up several pages. And if you're sloppy, or your work is disorganized, or your notation is not clear, it can be very hard to follow. Not just for the person who's grading your work, but for you. If something goes wrong and you have to go back and find a mistake, stuff like that can get really challenging unless you keep your work super organized. So try to mimic the way I write things here as you solve the homework problems. I think it'll help. The last call for questions on this guy. Any steps here we would like to take a closer look at? Okay. So the 2 other things I want to talk about are indefinite integrals and the substitution rule. Indefinite integrals aren't bad. Look, I think this is section 5.4. So we've been talking about definite integrals this whole time, which we can think of as areas. Indefinite integrals are just integrals, that long S symbol, without the A and the B. So the indefinite integral, this is definition, of a function little f is the infinite family of antiderivatives. For little f, denoted like this. So if capital F prime is little f, then the integral of little f, the indefinite integral of little f, we write as capital F plus c. And this is that whole infinite family of functions who have little f as his derivative. So in other words, it's the same thing as finding antiderivatives. When we were back in 4.9 and we talked about finding the most general antiderivative, we were writing down the exact same thing. It's just now we have this notation for it. So it's literally just a little bit of notation, new notation. If you see an integral symbol without the numbers here, we call that an indefinite integral. And the way you evaluate an indefinite integral is just find your antiderivative and then slap on a plus c. So for example, the integral of x to the 5/2. This would be a power rule thing. I'll add 1 to the power. 5/2 plus 1 is 7/2. So this is x to the 7/2 divided by 7/2 plus c, which you'll see is 2x to the 7/2 over 7 plus c. Or the indefinite integral of secant theta tangent theta d theta, we would take our most general antiderivative for secant tangent, which is secant theta plus c. So really nothing new here. Indefinite integral of 2 plus e to the x dx. We would split that up as the indefinite integral of 2 dx plus the integral of e to the x dx. An antiderivative for 2 is 2x. An antiderivative for e to the x is e to the x. And then we add on our plus c. All right, so nothing crazy here. It's just a new bit of notation for discussing antiderivatives that allows you to kind of connect the integral to the antiderivative in the way that we would like to. So we normally, when we talk about a definite integral, we cook that up by using an antiderivative and then evaluating between two endpoints. If there aren't any endpoints, then you just cook up your antiderivative and you write it in the most general form possible. You slap on that plus c. You only ever need one c. So if you have something like this where you split it up into 2 or more pieces, you can wait to write your plus c until the very end and you only need to write 1. Like we don't need to write a c for this and a c for this separately. And the idea here is that this isn't a single function. For every real number c, you get a new function. They're all vertical translates of each other, right? Like adding 1 to a function shifts the graph up, that sort of thing. These are all vertical translates of each other. And there are some ways you can think about this in terms of what they call direction fields. So I think probably you'll see a little bit of those here. Yeah, we can restate all of our antiderivative rules in terms of the indefinite integral. And that's really the value of this section, is just getting you more comfy with antiderivatives. And here's what I'm talking about with the vertical translates. So there are some fun trig problems. You can use your algebra or trig identities to break things up. Net change theorem is boring. We don't really care about that. So that's genuinely this whole section. The more interesting thing is this. And this is the last hard thing I'm going to require you to learn in this class. So I'm going to leave it here so that Wednesday and Friday we can talk about the substitution rule. But I would like for you to read section 5.5, okay? Go into the textbook and read this thing. That way when we go over it on Wednesday, you won't be seeing it for the very first time. This is a tough section, and not every Calc 1 class gets through this, but my Calc 1 classes get through this. You need to understand this stuff. Your Calc 2 professor will be assuming that you learned this shit and learned it well, even though a startling percentage of Calc 1 classes do not talk about it. So it's a little bit tricky. It's a way of making a change of variables in an integral. And the catch is this little dx piece, you have to change him also. And that can be challenging sometimes. So please read section 5.5, maybe even before you get into the homework. So the homework for this week will be opening up in just a little bit. And remember, it's going to be serving double duty as your homework for this week and for study guide 3. And the hardest problems in there are certainly going to be coming from section 5.5. So you would do yourself a nice favor by reading section 5.5, if not today, at least before class on Wednesday. That way, when we get in here, it won't be super scary and new to you. You'll be able to make sense of it. There are some functions we haven't been able to integrate yet, like tangent, that we will be able to integrate once we have this rule.
Is that the same as U substitution?
It is, yes.
Cool, thank you.
Alrighty. So I'm going to go ahead and end the meeting here. I hope you guys have a lovely rest of your afternoon. If you want to talk with me about any of the exam stuff, you can come and see me in office. Oh, wait, actually, hold on. I have to take my dog to the vet today. He got a nosebleed. So if you want to talk to me about any of the exam stuff, please send me an email. We'll try to set up some alternate office hour, but I cannot guarantee that I'll be in my normal office hour this afternoon. I'm going to try to get them in as soon as I can. May have to cancel that, but I'll make a post letting you guys know either way. Some
Professor.
questions in chat. Square next question, yes. Zach asked if we're going to be doing any sort of review for the final on Friday. Friday, we're still going to be talking about the substitution rule. I imagine we're going to want to spend a little bit of extra time on it, but I can probably organize a review for the final sometime over the weekend. So if you would like that, send me an email or a Canvas message. And then Krishna, you had a question also?
Well, can you extend the homework for last week? Maybe like a few days.
Submit an extension request and I'll get in there.
Okay, thank you.
Of course.
Kristen, just so you know, you can work on it even if he hasn't extended it yet and still watch the videos and all that stuff.
Yeah, I was just gonna do that and wait until he extended it.
Yeah, okay, I didn't know if you knew. I just found out recently, so.
Thank you.
That's good to know. I didn't know that either. All right, cool. So then I will see you guys hopefully this afternoon in office hours, but if I'm unable, then we will figure something else out. Take care.